Dear learners, in our previous session, we have discussed about general properties of group 15 and nitrogen. Let us take our discussion further. In this episode, we will be discussing about compounds of nitrogen. After this discussion, you will be able to elucidate the structure of ammonia, oxides of nitrogen and nitric acid, explain the method of preparation for ammonia, oxides of nitrogen and nitric acid, describe the physical and chemical properties of ammonia, oxides of nitrogen and nitric acid, appreciate the uses of ammonia, oxides of nitrogen and nitric acid. Let us start our discussion with an important compound of nitrogen, that is ammonia. Ammonia is a colorless gas with a pungent odor. You might have seen bottle of ammonium hydroxide in chemistry laboratory, which is solution of ammonia. As you can see on the screen that the molecule of ammonia has trigonal pyramidal geometry with the nitrogen atom at the apex. It has 3 bond pairs and 1 lone pair of electrons. Ammonia is present in small quantities in air and soil, where it is formed by the decay of nitrogenous organic matter such as urea, which on decomposition produces ammonia with carbon dioxide and water. In laboratory, it can be prepared by reacting ammonium salt with alkali, as you can see the equation on screen. Ammonium sulphate reacts with concentrated sodium hydroxide and form ammonia along with sodium sulphate and water. Let us prepare ammonia by adding concentrated sodium hydroxide solution into a pinch of ammonium salt, that is ammonium sulphate. When we add a pinch of sodium hydroxide solution to ammonium sulphate, ammonia is formed. We can smell pungent smell of ammonia, and we can further confirm it by bringing a glass rod dipped in dilute hydrochloric acid. You can see dense white fumes. These indicate the formation of ammonium chloride, which confirms the evolution of ammonia gas. On commercial scale, it is prepared by reacting dihydrogen and dinitrogen in presence of catalyst iron oxide with small amounts of potassium oxide and aluminum oxide as promoter. This is known as Haber's process. Observe the reaction involved. It is reversible and forward reaction is exothermic. Now, let us recall Le Chatelier's principle. Equilibrium will shift in forward direction by lowering temperature and by increasing pressure, but too much lowering of temperature will slow down the reaction. This we cannot afford when doing on commercial scale. So, optimum temperature chosen is 700 Kelvin. Similarly, pressure can't be increased beyond a limit. This may burst the container. So, again an optimum pressure chosen is 200 atmosphere. Let us discuss about properties of ammonia. Ammonia is highly soluble in water due to hydrogen bonding between ammonia and water molecules. Its aqueous solution is weakly basic due to the formation of hydroxide ions. It behaves as a Lewis base due to the presence of a lone pair of electrons on the nitrogen atom. It donates the electron pair and forms complex with metal ions. Hence, finds application in detection of metal ions such as cupric ion, silver ion. Let us perform one interesting activity. For this, we have concentrated ammonia solution and a clear light blue aqueous solution of cupric chloride. When ammonia solution is added to aqueous solution of cupric chloride, we have this clear light blue aqueous solution of cupric chloride, and this is concentrated ammonia solution. When we add this concentrated ammonia solution to this cupric chloride, these light blue precipitates of cupric hydroxide are formed. Further, addition of ammonia causes the copper ion to go back into the solution as a deep blue ammonia complex. When we keep adding this concentrated ammonia solution, deep blue copper ammonia complex is formed. This shows ligating behavior of ammonia. This activity shows that ammonia is a good ligand and makes complex. Ferrous ion forms a dirty green precipitate with ammonia insoluble in excess ammonia. Ferric ion forms a brown precipitate insoluble in excess ammonia. Now, let us discuss about uses of ammonia. Ammonia is used to produce various nitrogenous fertilizers like ammonium nitrate, urea, ammonium sulphate, and in the manufacture of some inorganic nitrogen compounds, the most important one being nitric acid. Liquid ammonia is used as a refrigerant. Now, we will discuss about oxides of nitrogen. 5 different oxides with all oxidation states of nitrogen from +1 to +5 are nitrogen oxide, a colorless gas formed by decomposition of nitrate salt; nitrogen monoxide, also a colorless gas but paramagnetic due to the presence of unpaired electron in it; nitrogen trioxide is a blue solid, while nitrogen dioxide is a brown gas which on cooling gets dimerized to form dinitrogen tetroxide. This tetroxide is colorless solid. Dinitrogen pentoxide is also a colorless solid. In dinitrogen pentoxide, you see that oxidation state of nitrogen is +5 because it has 5 valence electrons to be shifted to more electronegative oxygen, but it is making only 4 bonds, not 5, and this is because it has only 4 valence orbitals available for overlapping. Nitric acid is another important compound which is a highly corrosive mineral acid. The pure compound is colorless, but older samples tend to acquire a yellow cast due to decomposition into oxides of nitrogen and water. In the laboratory, nitric acid is prepared by heating potassium nitrate or sodium nitrate and concentrated sulfuric acid in a glass retort. On a large scale, it is prepared mainly by Ostwald's process. This method is based upon catalytic oxidation of ammonia by atmospheric oxygen. Nitric oxide thus formed combines with oxygen giving nitrogen dioxide. Nitrogen dioxide so formed dissolves in water to give nitric acid. It is a strong acid and concentrated nitric acid is a strong oxidizing agent too. It attacks most metals and non-metals except noble metals such as gold and platinum. The products of oxidation depend on the concentration of the acid, temperature and the nature of the material undergoing oxidation. Concentrated nitric acid forms nitrate and nitrogen dioxide with both copper metal and zinc. Dilute nitric acid reacts with copper to produce nitrogen monoxide and cupric nitrate, while with zinc, along with zinc nitrate, nitrogen oxide is formed. Concentrated nitric acid also oxidizes non-metals and their compounds. Iodine is oxidized to iodic acid, carbon to carbon dioxide, sulfur to sulfuric acid and phosphorus to phosphoric acid. Thus, from the discussion till now, we conclude that ammonia is a highly water soluble, pungent smelling gas and is basic in nature, a strong ligand due to the presence of lone pair of electrons on nitrogen and capable of forming complexes with metals. Nitric acid is an important industrial chemical. It is a strong monobasic acid and is a powerful oxidizing agent. Metals and non-metals react with nitric acid under different conditions to give nitrogen monoxide or nitrogen dioxide. Before we end the session, let me leave you with an assignment. Question number 1. Comment upon the optimum conditions for preparation of ammonia by Haber process. How concentrated and dilute nitric acid react with copper metal. Question number 3. Why nitric acid cannot be concentrated by distillation beyond 68%. Question number 4. Aluminium does not dissolve in concentrated nitric acid. Why? I hope you have understood the concepts discussed here and you are looking forward to discuss phosphorus. But till then, take care. I hope you have understood the concepts discussed here and are looking forward to discuss phosphorus. But till then, take care.